Okay, let's dive into what might just be the most famous equation in all of mathematics. It's the one rule that secretly connects simple triangles to, well, just about everything, from building a house to designing a video game. This is the Pythagorean Theorem, and it is the absolute foundation for so much of what we're going to cover in trigonometry.
But let's be real, why should we care about some ancient rule today? I mean, what does a 3,000-year-old theorem really have to do with the GPS on your phone? Turns out, there's a direct line connecting ancient geometry to that little blue dot on your map, and the connection is actually pretty mind-blowing.
So let's get right to the heart of it. You can think of the theorem as this unbreakable law of nature. But, and this is the important part, it only applies to one very specific shape, the right triangle. And there it is. A squared plus b squared equals c squared. Now, A and B are the easy ones. They're the two sides that meet to form that perfect 90-degree corner. We call them the legs. You can even swap them. It doesn't matter. But C is the special one. That's the hypotenuse. It's always the longest side, and you can spot it right across from that 90-degree angle. Getting C in the right place is the key to this whole thing. All right, theory is great, but let's put this formula to work. We're going to walk through a couple of examples to see how this simple equation actually solves real problems.
So here's a classic ladder problem. The wall and the ground make that perfect L shape. That's our right angle. The two legs are the height of the wall, 12 feet, and the distance from the wall, 5 feet. So we plug them in, 5 squared plus 12 squared. That's 25 plus 144, which gives us 169. All we have to do now is find the square root of 169, and that's a perfect 13. So the ladder has to be exactly 13 feet long. And here's a fun fact. 5, 12, and 13 are what we call a Pythagorean triple, a neat set of whole numbers that fit the formula perfectly.
Okay, so what happens if we know the long side, but we're missing one of the legs? This is where you have to be careful. The hypotenuse, C, is 25, and one leg is 7. So our equation is 7 squared plus b squared equals 25 squared. To find b, we got to do a little bit of algebra first. We rearrange it to get 625 minus 49, which equals 576. Now we can take the square root, and the square root of 576 is 24. The missing leg is 24 centimeters. And hey, guess what? 7, 24, and 25 is another one of those awesome Pythagorean triples.
All right, you're getting the hang of this. Let's level up. For this next one, a calculator spitting out a long, messy decimal just won't cut it. We are looking for the exact answer.
So this time we have two legs that are both 6 inches long. That gives us 6 squared plus 6 squared, or 36 plus 36, which is 72. So C is the square root of 72. Now here's the clever part. Instead of reaching for the calculator, let's think, is there a perfect square that divides evenly into 72? Yep. 36. See, 72 is just 36 times 2. And since we know the square root of 36 is a nice clean 6, we can pull that 6 outside the square root sign, leaving the 2 inside. And there it is, our perfect answer, 6 times the square root of 2.
Okay, you've got the basics down. But now let's talk about the important stuff, the common traps. Knowing these will help you avoid the exact same mistakes that almost everyone makes when they're first starting out.
This is the big one. The number one mistake. The formula is so simple and catchy, you'll be tempted to use it on every triangle you see, but you absolutely cannot. If you don't see that little box symbol in the corner that tells you it's a 90-degree angle, the entire formula is useless. It just won't work, period. And here's the other classic blunder. It's this illusion where it feels like you should just be able to take the square root of each part separately, but math just doesn't work that way. Let's prove it with a 3, 4, 5 triangle. The right way, 3 squared is 9, 4 squared is 16. You add them first to get 25. The square root of 25 is 5. Perfect. Now the wrong way. The square root of 9 plus the square root of 16 is 3 plus 4, which gives you 7. See, a completely wrong answer. So remember the rule, always add the numbers inside the root before you do anything else. Okay, so we've worked through the math. We know how to dodge the common mistakes, which brings us all the way back to the beginning. Why does this ancient theorem matter so much in our world today? Imagine you're in a city. You need to get from point A to point B. Let's say you have to go 3 blocks east and then 4 blocks north. You can't just cut through the buildings, so you have to walk the grid. That's 3 blocks plus 4 blocks, a total of 7 blocks walked. They actually have a name for this. It's called taxicab geometry. But a bird, or a GPS signal, doesn't care about streets. It travels in a perfectly straight line. And suddenly, that 3 blocks east and 4 blocks north aren't a path anymore. They're the legs of a giant right triangle. The direct distance, the as the crow flies path, is the hypotenuse. And hey, we've already solved this one. 3 squared plus 4 squared. Take the square root, and the true distance is just 5 blocks.
And that right there is the punchline. Every time your phone tells you you are 5 miles from your destination, it's not counting the roads. It is using the Pythagorean theorem to calculate that direct, straight-line hypotenuse. It's constantly running this ancient math over and over right in the background.
And don't think this is just a one-off trick. What you've mastered today is the engine behind other advanced tools, like the distance formula you'll use for coordinates on a graph. It's even at the very core of one of the most important rules in all of trigonometry, the Pythagorean identity, which is absolutely essential later on. So, I'll leave you with this final thought. We now have this perfect, unbreakable rule for right triangles. But what about all the other triangles? The ones that aren't so neat and perfect. Is there a rule for them too? Well, there is, but that's a story for another explainer.